I'm the chairman of this session, and we will start with Giacomo Roati from Lens for the first talk, and I'll give you a sign after 25 minutes.
Perfect. Okay, so good morning, everybody. Before starting, I really want to join the other speaker with thanking the organizer, of course, to have organized this very nice conference in such a place, and to give the possibility to speak about the results that we performed in last 2 years in Florence. So first of all, I would like to show the group. And about the work that I'm going to discuss today, I want to acknowledge Matteo Zaccanti, Giacomo Valtolina, Francesco Scazza, and Andrea Amico. And there are also other people, of course, that work and collaborate with us, and students that are also now in this audience, now in other groups. Well, where do we come here? Okay, so as you probably have seen from the title, I'm going to talk about some transport properties and transport measurement in ultracold Fermi gases. And this is just an introductory slide. So I think that the transport and out of equilibrium dynamics is a very important tool that allow to unveil and to disclose eventually some fundamental properties of materials, okay? And for example, some phase transition are really disclosed by studying transport properties. For example, superconductivity, superfluidity. And again, yesterday, Jora was mentioning about undersole localization. Also, the absence of transport, in some sense, can indicate that something is happening inside the material, and there is some macroscopic mechanism at the level of quantum mechanics. And of course, now, in the modern days, people are trying to engineering devices in which you can also study spin transport, or, again, transport properties can also show topological structure or topological transition inside material. Well, study quantum transport with ultracold atoms is a very hot topic in these days. I just add these slides just to more or less give you 2 references. That this is taken from this paper, and about cold atoms transport, I mean the work of Jean-Philippe Brantut and Tilman Esslinger in ETH. Here is just a table in which you can compare cold atomic properties with electronic properties. And of course, there are differences and of course some similarities. And of course, I mean, you can recognize in the case of ultracold atoms this highly tunable, that of course gave us the possibility to engineer transport and devices in a, let's say, easier way with respect to typical electronic system. Well, this is the outline. I will try to tell you about how out-equilibrium dynamics allow us to explore and to study some property of a strongly correlated Fermi system. And I try to be able to speak about both of the arguments. Anyway, I try to give you some flavor about repulsive fermions. And okay, Matteo probably is going to tell you more about it later. And about superfluid dynamics. And here is, I mean, the topic is very in strong connection with what Anna and Ervig were mentioning the last days. Well, what is the important, I mean, this is, I need to introduce this because this is the key point on which I will build up my contribution here. So, a Fermi gas close to a Feshbach resonances, the many-body spectrum of Fermi gas close to Feshbach resonances can be illustrated by this energy spectrum. Here it is the energy per particle, and this is the interaction parameter. As you can see, there are 2 energy branches. There is the red one that I call repulsive branch, in which fermions in 2 different spin states, they don't want to pair. And in particular, they can form a weakly repulsive or strongly repulsive Fermi liquid. And then there is the lower branch, that is the so-called BC-BCS crossover branch, which fermion can pair at equal 0 forming or molecules, or more exotic pair like unitary pairs or BCS like Cooper pairs. So anyway, what I want to point out that this is a very rich system because allow in principle to study both spin and superfluid dynamics. Well, and this is the only thing that I say about that. In the case of atoms living in this branch, if we crank up their repulsion, and this is, if you want, is the level that is critical around KFA1, then what could happen, in principle, is that the system could make a transition from a paramagnetic mixed phase to a fully ferromagnetic state. Okay, this is the so-called Stoner model. I will not enter in any detail more than this. The only point, of course, is that surfing on this repulsive branch means to surf in the excited state. Okay, and this what happens is that via 2 or 3 body recombination processes, due to eventually up-down overlap, density overlap, in a very short time scale, this branch is depleted when at very strong repulsion. Okay? Then it means that, in fact, the system will populate the ground state. Okay? Well, our system, this is my, let's say, experimental setup slide. So we work in a 2-spin state at the lowest, we call up-down. And then we work like many other groups across the BC-BCS crossover, so we can work with the molecular VC, a superfluid Fermi gas, and eventually at the unitarity. And then we can also produce ultra-cold Fermi gases in the weak interacting regime. Well, let's start with the part 1, that is to study what happens if I try to study the system in the upper branch. Well, if I can use, this is a joke, of course, but Stoner will tell us, let's try to reduce the density overlap, because the density overlap between up and down spin state is the one that is probably causing the decay, of course, or can enhance the decay in the attractive branch. So we decided to do this experiment. So we started with a ferromagnetic state that is artificially created. Okay, so we have segregate all the up particles here, all the down particles there, by a thin optical barrier. And the key point here was that the separation between the 2-spin reservoir was just few interparticle spacing, very cold, and this means that, in fact, this allowed to prepare the system in such a way that the density overlap was, of course, vanishing initially. This was suppressing completely the pairing effect. We can prepare adiabatically the system. This means that, given this initial separation, the two clouds, in fact, when the barrier is switched off, can approach very gently, okay? With relative momentum that is much smaller than the Fermi wave vector. Meaning that, in some sense, they do not do any bunching, strong excitation, like, for example, in Martinsville, an experiment at MIT of the spin collider, okay, like he was calling that. And this probably can also allow this way to reduce temperature and heating effect. Well, the measurement that I'm going to discuss with you is the measurement that takes the name of spin-dipole frequency measurement. So we wanted to study the out-of-phase motion of the two clouds once that the barrier was suddenly turning off. Okay, so we can, with a modulator, we switch off the barrier in time of 1 microsecond, and then we see the dynamics of this cloud. Why is interesting this? Well, because the spin susceptibility is directly related to the spin-dipole frequency. And here is the plot of the spin susceptibility that you have versus the interaction parameter, renormalized by the one of an ideal Fermi gas. And you can see as I increase the interaction, so this 1 over KFA, so 0 is the resonance, then it's expected that the spin susceptibility should increase, and correspondingly, the spin-dipole mode frequency should decrease with softening. Well, the other thing that is very interesting is that if I do the same thing in the case of a lower branch gas, then of course you expect, and these are just two theories, but for the moment it's not important just to see the trend, we see that the spin susceptibility should decrease, in fact vanishing in the superfluid state. At the same time, the spin-dipole mode frequency should increase. Well, then the measurement is performed like I said, so we prepare these two reservoirs, we turn off suddenly the barrier, and then we study the dynamics. And this, for example, is the dynamics, the center of mass motion versus time. And you can see that we see a decay, and on the decay, on top of the decay, we have a modulation. Okay, I will not have time to tell you, but anyway, the decay, you can easily convince that a long time will give you us the measurement of the spin drag, okay, of the two clouds, because this is what you expect anyway. Well, this is a set of measurements that we did. So this is, I am plotting here the distance between the two centers of mass versus time for different interaction from low to high. And I summarize this in this graph, in which I propose, I show you the spin-dipole frequency that we extract from here versus the renormalized by the trap frequency in that direction versus KFA. Well, just concentrate on the blue point. So we start, of course, to see that the frequency decrease. Around 1, there is a jump. Let's say physically we are not able to feed the data in this region here. But after that, the data start to, the frequency, the spin-dipole frequency acquire a value that is more or less corresponding to two clouds that are bunching one against the other, okay? Just in penetrating. The green line corresponds to the theory that, Alessio Recati gave us in the case of 100% overlap and 25% overlap. So our data more or less are in the center of these two. I mean, this is just to give an idea that we are in quite good agreement with theory also. And the pink point, the purple point, sorry, corresponds to the same measurement done at high temperature. And you see that qualitatively that the transition to this, let's say, bunching regime appears at larger interaction, repulsive interaction. This also makes some sense, okay? Colder, smaller interaction, hotter, higher repulsive interaction. Well, okay, was not just to satisfy a referee, of course, but we wanted to do the measurement in the lower branch. So let's suppose that we start to work in the lower branch. What is happening? Well, we can prepare the gas there. And then what we see, we measure the same quantity, again, versus the interaction parameter. And now you have to see the red point. As you see from the red point, we see that the spin dipole frequency, in fact, increased. Actually reach a value that is almost 3 times the trap frequency, so something that is really exotic. Anyway, and the red points are, I mean, we can extract this using data from Tajima and Ohashi for the lower branch spin susceptibility. So the message that I want to convey you is that despite is very unstable, the upper branch, in fact, anyway, the dynamics that we are observing is really repulsive driven. Okay, so we are working, at least initially, the system is really in the repulsive branch, even a very strong interaction. Well, let's go in the other direction now. So let's flow down, I mean, now in the attractive branch. And here, for do the measurement of Josephson dynamics in real experiment, of course, in the atomic case, we need to be very thin and cold, okay? Anna was showing, of course, the barrier. We cannot be at the level of one correlation length, like thickness. So anyway, we try to be as tiny as we can, as we could. So why, okay, I don't probably need to motivate in front of you why it's interesting the Josephson effect, but I believe that this is really a very fundamental phenomenon, and in fact is the one that can link superfluidity and phase coherence in one measurement. I mean, using the words of Phil Anderson, Josephson effect is the tool to pinpoint the order parameter of a superfluid state. And in fact, you can convince yourself, because while phase is not, the absolute phase is something that is not very well defined, of course, the order parameter is related to the density of superfluidity or superconductor. Then, of course, if you split your superconductor into the two parts, then in fact it's like to study with the Josephson effect the interference of the order parameter. So it's like, it's a very nice and powerful mechanism that gave you then access to the relative phase dynamics between the two superconductor or two superfluid. Well, we'll not enter in any detail about this, but this also is interesting because Josephson junction, and this Herwig was mentioning in some way, are also the building block to study other kind of phase transition. It can be also dynamical phase transition, but related to Caldera. I mean, I was seeing him around here. Caldera was here in these days. And of course, based on the Caldera-like model, in which you have dissipation and superconductivity working, and superfluidity, if you want, working together. For example, an example is the very famous superconductor or superfluid to insulator transition, I mean, that you can, I mean, write down in terms of Josephson dynamics, okay? Well, in our experiment, this is our junction. So this is our superfluid that can be a BC or a unitary Fermi gas or slightly BCS. We segregate, I mean, we just cut in two parts. And then we study the evolution of population and phase. I will not enter in any detail because Anna was very good in giving me this introduction. Of course, just to know that if tunneling dominates, then you should see Josephson oscillation. If interaction dominates, in the case of atomic system, you should see the so-called macroscopic self-trapping. Well, these are observable. As I said, we can measure the population and phase, just study the time of flight picture. So a few years ago, we were in fact observing the transition, the Josephson dynamics in the case of molecular BC and unitary Fermi gas, both in population and both in relative phase. And mapping the phase, we could observe the pi/2 shift between population and phase, indicating that the system was in fact performing Josephson dynamics. Well, okay, now we come to the point. Of course, since we are playing with atoms, we can tune the relative imbalance between the two well with very high degree, of course, because we just need a different preparation. This means that in principle, I can increase the so-called bias potential. So I just increase the spin imbalance, the population imbalance. Well, this, for example, is an example of 20%. Well, if I increase the the population imbalance, then I could arrive to a point in which I increase the ratio between the charging energy of the system in some extent and the Josephson coupling energy. And the system here is expected to enter, in case of bosonic junction, to macroscopic quantum self-trapping state. That it means the phase should run, so no more oscillating, so linear increasing, with a rate that is proportional to the charging energy that you have in the system, okay? Well, what we see is not, in fact, because we don't see that, because we have, in fact, we enter in a regime of dissipation driven by phase slippers at a rate that is just given by the Josephson-Anderson relation, so it's just proportional to the difference in chemical potential that I can control at the beginning divided by the Planck constant. Well, I want to tell you that the macroscopic quantum cell trapping is pretty pathological of atomic system, because in fact in real system does not exist, because in the case of superconductor, to arrive to this point of imbalance, you probably before you break the Cooper pairs. And in the case of helium, in fact, what they see is more or less the same, because when they start to have two helium reservoirs, they can create a fixed different pressure between the two reservoirs connected by a channel. What they see is that the velocity, of the superfluid, in fact, is behaving in this funny way, so it's increasing and then oscillating in this sawtooth behavior at the frequency that is, in fact, given by the difference in chemical potential. So in that case, it's the different pressure between the two reservoirs. And this was explained, this is not something incredible, because it was, in fact, predicted by this guy, Anderson, just because, when you have a superfluid flowing through a channel or an aperture, then for geometrical constraint and something that is still not fully understood, I would say, in the sense of which is the velocity that is driving this. But anyway, the superfluid reach a critical velocity, and then you form vortex. When the vortex cut the flux of the superfluid, then you have a phase slip. And this is the way in which our system, the superfluid, is able to not access to infinite or infinite velocity, because, of course, given this relation, the gradient of this will give me the velocity. So in principle, this tells me that the superfluid could access infinitely large velocity. But this is not the case, because then you form vortices, and then this vortex just create phase slip and reduce the velocity in a quantized way, if you want. Well, what we can do in the experiment, again, we can increase delta mu, and the nice thing is that we can do in all the superfluid that we have. So we can do in the BC, in the unitary, and the BCS. And again, these numbers, just to tell you that, okay, a key point is that we don't never access the region in which the difference in chemical potential is larger than twice the gap. Okay, in the case of BCS, of course, or in the unitary. Because we want to be just, we want to increase, but not to enter in a regime in which we can have also some other effect. Even though, I will tell you, probably we anyway see some effect of pair breaking. Well, this is the dynamics that we see. So this is population imbalance. This is time for BC, unitary, and slightly BCS superfluid. So we see initial decay, and then oscillation around the zero imbalance, okay? What happens here? Well, what we did then, since we have the nice thing, maybe sometimes we forget, we have a gas. So the gas can expand, okay? So we can switch off the trap, and we can see what is happening in time of flight. Okay, you cannot do it with a superconductor, of course, this, okay? So then expanding the gas, what we see is that in this, and then I will superimpose, but in this region here of time, we see vortices appearing inside the superfluid. These are produced stochastically. They have different shape, but for me this is not relevant. And if you want, what is important that is the number of these vortices increase going from the BC to the BC-BCS crossover. And this makes sense because, again, the Phil-Anderson relation tells me that the phase slippage process should increase like the chemical potential difference. Well, then, yeah. Oh, sorry. No, this is N is the total, is the N1 minus N2 over the total, is the imbalance. Yeah, but it's correct, just because it's good. The vortex moved from the high to the lower chemical potential. Well, the nice thing, okay, if you want, the messages that we can extract from here is the following. The system is initially decaying. The current is some sort of DC current. Then after that, the system itself is able to decrease the chemical potential enough, then the system is able to reperform Josephson dynamics. So, I did not tell, I tell now, the oscillation that we see here are in good agreement with the one that we were observing in the case of Josephson dynamics. So the system is releasing the extra energy true vortex, but these are not infinite vortex numbers, so just a few vortex. And meaning that the main superfluid is not really affected so much, okay? The bulk, there is no problem. And then the system is able again to perform Josephson dynamics. So the nice thing is that we can see the same. Okay, this is just for a BC. I think that this is not very high barrier, but just to give you the flavor, you can see that you have initial decay, then oscillation, and the phase is doing some sawtooth behavior or some dynamics between pi and minus pi, but then also the phase starts again to oscillate, out of phase again with respect to the population. So Eric was showing how we can model his dissipation. So since this was a junction, in some sense close in our picture to something happening in a superconducting junction, then we decided to use a model that is very well known in the case of superconductors, okay? That is the so-called resistively shunted Josephson model. Well, to apply this model, you must be in a ohmic condition. So this is why we measure voltage-current relation. These are data, these are the derivatives. So this we can plot I versus delta mu over H. And then we see a line, okay? This means that the system is behaving like an ohmic metal, meaning that now I can try to apply the equation that are given by this model. And these are phenomenological equations, so the resistance that is here is including all the possible mechanisms that happen. It can be pair breaking, can be vortex, can be everything, okay? So it's just very phenomenological. But this gave us the possibility then to measure G, to extract G, okay? And then the current. Well, this is the plot of G that we get in a unit of the Planck constant versus V0 over mu, and for different superfluid from BC, unitary, BCS, and then this is really is a very cold but not superfluid, because for sure at this value of KFA we are not there. And I want to just this slide I put because I found that sometimes maybe it's basic what I'm saying, but it's interesting anyway. Look this number. These are 10 to the 3, 10 to the 4, 10 to, this is scale. And look, compare this with the conductance taken in the case of a quantum point contact in ideal fermions by Tillman Esslinger and Jean-Philippe Brantut, where they see the quantized, okay, conductance, and these numbers are 2, 4. This means, in our case, what is tunneling are bosons, are pairs, okay, for which there is no constriction in the number of fermions or particles that you can put in the conductive mode. Well, and this I come almost to the end, so don't worry. So we wanted to plot this conductance in a more, let's say, maybe universal way. And for this, we use the extended Thomas Fermi model that, in collaboration with Andrea, Xenia, and Nick Proukakis, Gladia, not Xenia. And to test this, what we did was to use the model to fit the density profile of our system to extract the density below barrier. We are not able, for resolution in that moment, to measure directly. Then, if I do this, I can plot G in all the regime versus this and 0. And I see that all the data set are aligned on the same behavior. Then, what I can use is I use a model that, in fact, was proposed by Bill Felix, Gretchen Campbell in NIST, just saying that the current and then the conductance should be proportional to the number of phase leakage, so the rate of phase leakage, times the number of particles participating to these events. Well, we fit this data, it's almost linear, and we see almost one in the case of BC and unitary Fermi gas. I'm not claiming anything except then. We see something larger than 1 in the error bar. In the case of BCS, as if something other mechanism in the BCS gas can happen. Eventually could be pair breaking, but we don't know. But anyway, the message here is that we see the same dissipative mechanism in all the BC-BCS crossover for our system. If I increase much the interaction, again, the chemical potential difference, I enter in a regime that is very different. So if this is Josephson, this is what I discussed about, and this is what we see now. So we see just a discharge at 0, arriving to 0 difference in chemical potential. And if I plot G, we see for both the BC and for the BC and for the unitary gas, we see that we have an initial behavior. This is the region that I talked so far, and then we have an increase. And at the same time of the resistance, okay, this is it's 1 over. And at the same time, the number of vortex versus this quantity, so the relative chemical potential, also show an increase. for sure we see clouds with like 10 vortex, 8 vortex, so something happened there. And okay, so one pictorial way could be that, of course, since we have many vortices, these many vortices can in some way scramble the relative phase between the two superfluids, of course, in the barrier region. And eventually what you can see that EJ eventually is decreased, even though I can tell you the bulk is still superfluid. So what is happening is the dynamics below barrier. It's like if below barrier, the vortex or the interaction between vortex, this is still something that we have to understand, is creating a situation for which the two phases cannot be connected like before. But this is completely open. What we are doing now? So in the last months, we installed finally an high-resolution achromatic objective. These are the numbers, so we can arrive to something like less than 1 micron at 670, around 700 nanometer. We have our happy DMD, and now we are able to imprint sharp potential that can be also disorder in case on our cloud. And finally, we have also now, finally, almost installed the TM01 to create a 2D system. Okay, so this is what more or less we are going to do. So we are going to study transport in 2D with and without disorder in some geometry that we are arranging. Just one slide more. I want to tell everybody that I'm very proud to show that we have now a new BC-BCS crossover in Mexico City. These are like 2 weeks ago data. And okay, the guy that has a very strange face here is Professor Seman that is leading the group there. So this is another BC-BCS crossover in Mexico City. In fact, it's the first in all Latin America, by the way. And that's all. Thank you so much.